Welcome, everybody in the lecture hall. Welcome, everybody on Zoom. Welcome, everybody watching us from the future. So what better way to start than with a question to see if you remember what I told you last time. So what is the size of a block in HDFS? I need to click right here. And there you go. Oh, sorry. So there seems to be already a majority. And the majority is correct, even though we have here somebody very enthusiastic about big data, several people. All right, so indeed, the blocks in cloud storage, so in a distributed file system, they are much larger than the blocks you have on your disk, right? So the scale is roughly 1 gigabyte, right? So 128 megabytes for HDFS, 4 gigabytes for Azure Blob Storage. It's all the same. It's the same order of magnitudes. This is to be contrasted with the size of a block on your drive, which is around, so let's say very roughly speaking, 1 kilobyte, 4 kilobytes. And by the way, the page blobs, because some people asked of half a kilobyte, so 512 bytes, it's the same order of magnitudes than those on your laptop, because again, the point of having very small blocks like 1 kilobyte is random access. Read and write random access. So this is why they're super small for page blobs and for the file system on your laptop. But for systems like Azure Blob Storage or HDFS, they need to be much bigger because we are going to massively query data, large quantities of it. And so with this size, we are able to actually do that. Just that you understand why we do not use 1 kilobyte blocks in HDFS. Imagine that you have to read an absolutely gigantic file of 1 petabyte, all cut in blocks of 1 kilobyte. The number of times you would need to access a block would be so gigantic that you would spend your time in latency waiting for the blocks. So that's the reason for this order of magnitudes. All right. I have another question for you regarding HDFS. Remember the architecture with the name nodes and the data nodes? Well, the name nodes without an S and the data nodes. So imagine we want to do two things. So one is we want to create a directory. Another one means we need to get the data, insist on the data for a single file, for getting the data itself. So do you communicate with the name node, the data node, both of them, then in order to do what? We have a majority here. So indeed, when you create a directory, you need to communicate with the name node. You also need to communicate with the name node to signal your intent to read a file and to get the blocks if you don't already have the block IDs. But to get the actual data, the actual contents of the blocks, then that comes from the data nodes. You need to directly connect to the data nodes. Okay, so this is good. We have a majority on this as well. And this is where I left you last time with this big cliffhanger. We looked at what to do to eliminate the single point of failure. The first thing we did is we persisted some of the information in the memory of the name node. That includes the file namespace, so the directories and files. That includes the mapping from the files to the block IDs. We did not persist the mapping from the block IDs to their locations because we get them anyway in the reports. So that's the reason we don't persist that. The second thing we did is we backed them up, right? So we persist them to disk, but we also back them up just to be sure that we don't lose that at multiple places like S3, Glacier, and so on. And then came the next question, what happens if it actually fails? So we have done that. We have persisted everything, backed it up, and it fails. What do we do? We start it up again, right? It crashed. We just start the name node again. So let's do this. So remember that since we started again, we need to restore the state. So the state was saved to, among others, a namespace file. So that was a snapshot of the namespace. And remember that whenever we created new directories, created new files, we didn't modify this namespace file. That's an old snapshot. Instead, we just have an edit log. It's similar to Git when you have revisions. You don't actually update in place, you just create new revisions. So we had this edit log. So what do we do now that it has crashed? Well, we take that namespace file, we restore it into memory, and then we have a file system. I just need to turn that a little bit because otherwise there's artifacts of the projection. So we restore the namespace file all the way into memory, including the tree of directories and files and the mapping to the block IDs. And then we play the edit log. I have this little play here. So we just play everything that changed later. We just go through the edit log and play through it, right? And now we have the last known states of the system. What about the locations of the block IDs? Well, here we just ask for a report from all the data nodes, and so we receive them via the data node protocol, right? So they will all connect because they send heartbeats, right? And so in the heartbeats, you can say, oh, please all send me a report. So now we have the block locations. So now we have restored, who agrees? We have restored the state of the name nodes. But you see the problem, that's the time it takes, because that can be like half an hour doing all of that. So the whole system is not available during that time. That's not so great, right? Everybody has to wait until this is done. So can we do better than that? And indeed, yes, we can do better than that. And this is called high availability. That's the code name that the HDFS team gave to these efforts. And so yes, can we do better? Of course we can. One thing we can do better is that when the edit log grows, because we changed a lot, after several days, several weeks, several months, the edit log is going to grow, and that only makes it worse to recover. So what do? We just do a checkpoint. Periodically, we just put it back into a single snapshot at a later time, and now we again have an empty edit log, and we do that periodically. Okay, so this is one way of shortening the time that it's going to take to start again. But there is even better than that. We have what are called standby name nodes. Standby name nodes are other machines that also run the name node process, but in standby modes. They don't actually do anything or interact in any way with the clients. They are just here, ready to step in if the name node has failed. And since they follow the modifications of the file namespace and the mappings to the blocks and so on, they always are up to date with this. So it's almost instant. The name node fails, another standby name node just takes over and it continues, right? For whom does that make sense? Right? Okay. You can have several of these. Just a few words about how they sync, because the standby name nodes, they need to be in sync on this same data. There's different ways of doing that. One way I put it here is a network attached storage. They just are connected to a drive that they will see. Since it's a small number of machines, it's like 2, 3, 4, 5 machines, then that's okay, right? They can just connect to some network attached storage. It's not a lot. Or a quorum journal manager. Quorum, that's the same quorum as we saw in Dynamo, right? Remember in Dynamo, it was the sloppy quorum because it's we tolerate partitions, but here it's a strict quorum, right? That's a there's no partition. It's such a small amount of machines that you don't really need to deal with that sort of things. So we just have a quorum journal manager, and they just agree on the latest version in that small number of machines, right? So we have the same R plus W greater than N, except that this time it doesn't break, or there's no sloppy quorum or anything, right? You can watch an answer that I sent just earlier today to a question in the forum explaining sloppy quorum. All right. So what else can I say here? Well, that's pretty much it. What I can say too is that this is pretty new, actually, that we have these standby name nodes. In the past few years, Actually, it's almost been like 20 years now. There's been a lot of intermediate versions of that. We've had checkpoint nodes, we have backup nodes, we've had secondary name nodes, so all kinds of things. But the standby name nodes, these are the ones that now are the most fancy version of this high availability. Plus, there is one more thing. It's that these standby name nodes can also be promoted to so-called observer name nodes. What it means is that if people just want to read HDFS, then they can also connect to this. It means that you're doing some load balancing for the reading things. If you want to just list the contents of a directory, read a file, know where the blocks are, then what's new with observer name nodes is that the clients can connect to any of them, not just the name node, but also the observer name nodes, only for reading. Okay, who is still with me? Okay. And finally, we have one more fancy thing, which is called federated HDFS, federated distributed file system. Here, maybe the best way to explain it is, who of you have already installed Linux in one way or the other on your machine, right? Who has already, or remembers, I don't know if now it's maybe more automated today, but at some point you decide on the partitions, and then you say slash goes here, slash home goes there, the swap goes there. Who has already seen that? Right? So it's pretty much the same thing. We can also divide the namespace in such a way that we say this name node right here is responsible for this part of the hierarchy and this other name node for this other part of the hierarchy. And that also kind of does some load balancing, but here based on the splitting the namespace, right? Okay, so I'm actually done on explaining physically how HDFS works. So now you know how we have high availability, and even if the name node crashes, we can very quickly recover thanks to the standby name nodes, and we can even spread the load with the observer name nodes and the federated file systems. Now, just a few last words. I'm almost done with HDFS. How do we use it? Well, we, of course, are going to use it with MapReduce and Spark later to query. But in fact, since it's a file system, you can also access it via the command line, right? I'm assuming you all know on your local laptop, cd, ls, all of these commands, right, to interact with the local file system. Well, the way you do that with HDFS is exactly the same. You also have commands that follow a similar standard, POSIX. And the way it works is that you have the Hadoop fs command or the HDFS DFS command, followed by what you want to do, right? So just that I explain the difference between the two. The HDFS command here is really specific to only HDFS. It doesn't know anything else, right? And then with HDFS, you can create directories, read the content of a file, copy files, and so on. Hadoop is a more powerful command that is a wrapper around not just HDFS, but also S3. So Hadoop can also connect to S3, to Azure Blob Storage, to all kinds of places, to your local file system, and so on and so on. It's like a super command that just connects to anywhere you want in a similar way, right? So this is why it's more popular to use Hadoop than HDFS, because it can just connect anywhere. Now, these are concrete examples. So how do you list the contents of a directory? ls, right? And you just do it with a -ls after Hadoop FS. How do you display the contents of a file? cat, right? The same way you do it on Linux. Then remove a file, delete a file, it's rm, mkdir for creating a directory, and so on. So that is the POSIX, very similar to the POSIX standard, and you can use all of these commands. But there is one difference, is that it's going to take a while to execute them. On your local laptop, you press return, it's almost instant. But if you do this with HDFS, you're going to notice there's 1 or 2 seconds until it returns. And again, this is why we have these blocks that are much bigger, because now we have a cluster of machines. So instead of a few milliseconds, now it's a few seconds every time you do something. Okay, so you just have to have this intuition. But you see, it's kind of an example of data independence in itself for a file system, right? Because we, again, have a similar interface with it than you would have on your machine, right? So this is for working with the file system. What about uploading and downloading? Well, you have special commands for that. There is one called copy from local. This one is to upload something from your local drive all the way to HDFS. So you use -copy from local. And to download, it's copy to local, right? You just take a file and download it. Of course, that only works for small files. If you take a file that is a petabyte long, then of course you cannot download it. And you can also not upload it because it wouldn't even fit on your laptop in the first place, right? So that is only for the files that fit also on your laptop. So upload, downloads. Now, one more thing in here, we just have these absolute paths that kind of implicitly imply that you're on HDFS, right? This is a directory on HDFS right here. So it's implied because HDFS is configured as the default file system. And for this, you have actually configuration files. If they are a bit hidden, it's called core-site.xml, where notably you can say that your default file system is HDFS. This is the host for the name node and the port on which it listens. And that's just a description. So basically, you just say, my default file system is this. So whenever now you use the Hadoop FS command and you just say / blah, 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 without specifying if it's HDFS or S3 and so on, then it's because it's configured in here. But of course, if you do want to access something else or HDFS is not the default, then on this, instead of the / you would have the full URL HDFS : / or S3 : / or S3A : / I can't remember the one for Azure. There is also one with some WA and so on. So there is also a URL. So you just put the full URL, including the host name and the port, and then followed by the absolute path, right? You can also use relative path, and then that's just the semantics of a working directory, right? You have a working directory, and if you have a relative path, then that's going to be relative to that directory, right? Any questions? Questions? This is another example of configuration file. So this is HDFS site. So core site is like common to all of Hadoop. So this will also be seen by MapReduce that would also do that. You can also change in the configuration files, for example, the replication. So here you can set it to 1, 2, 3. So the default it's 3, but you can change it. You can also configure the name of the local storage of the name node, you know, where it stores and persists things. The same for the blocks, for the data node. And in fact, for those of you who feel adventurous, you can try to create an HDFS cluster on either Amazon or Azure, and then SSH your way to one of the data nodes and try to go to that place and see if you see the block files. Right, that can be a nice exercise. I think the TAs might even have, I don't know if it's still there, but a Docker that simulates HDFS as well, that you can also use to play a little bit. All right, so that's just a small reminder that even though it's a distributed file system that is very fancy with petabyte files, in the end, everything is really stored on good old hard drives like the ones you have on your laptops. Right. So a few more words. I already warned you about the terminology. It might be different. So the original Google file system said master instead of name node. They said chunk server instead of data node. They said chunk instead of block. They said checkpoint image instead of FS, I don't know where, file namespace image, FS image. And they said operation log instead of edit log. But you know, these are just names, right? So just expect that people might speak different, might use different terminology when talking about the same thing. It's the ideas that matter. All right, something else that is different, as I already told you, is the size of the block. There's distributions of Hadoop like Cloudera that have a different setting. They use 64 megabytes. I think GFS was also on 64 megabytes. I told you Azure is now on 4 gigabytes for the size of the blocks. You know, things keep evolving. And as the hardware is evolving, then these numbers are also going to probably evolve a bit. in a few weeks, we'll start querying data. And so you need to be aware that what we will store on HDFS and S3 and Azure Blob Storage might be raw data that you directly get from CERN or from the satellites in space, but it could also be derived data, meaning that you queried the data that you received from CERN and you save intermediate results. We will see how, and that also is going to be data stored on HDFS, right? So it's not just the original data sets that we're going to have on HDFS, we will also have the intermediate data sets that were built with MapReduce or with Spark, right? So I just like to use this wheat and flour representation for the original data and the one that you have created. There were a few very nice questions that I think, Dalia, you received, and you shared them also with everybody. So I want to insist on one because that's a common one. What's the point of block storage? Because I told you S3 doesn't have block storage. I told you Azure Blob Storage has block storage. I told you HDFS has block storage, but not S3. There are no blocks in H3. And the limitation, there's two advantages of blocks. The first one is that because you don't have any blocks in S3, an object can be at most 5 terabytes, right? So something that fits on a machine. On Azure, since you have blocks, you can have almost 200 terabytes for a single object, right? So the size of the object can be much, much, much larger if you have blocks that are exposed via the API and part of the model. An advantage of this is about the locks and data consistency, because you might remember that I mentioned when you read or not read, but when you write a file in HDFS or when you append, at the end of the file, you take a lock on that file. Nobody else can write at the same time. And that actually matters if you have a data set stored as a single huge 200 terabyte object in Azure Blob Storage, or a data set that is stored in thousands of 5 terabyte files in S3, right? It makes a difference because when you access the data set, that's called sharding. If it's sharded in smaller objects, you only lock one object at a time. You cannot lock the whole data set. But if your data set is a single huge 200 terabyte object in HDFS or in Azure Blob Storage, then you can be guaranteed that you're the only one to modify it at any time. So that is one benefit of block storage. That is a consequence of the first benefit of larger objects. For whom does that make sense? Yes, all right. I think this is the last slide. It wants me to click today. So I want to check where you are now with HDFS. That looks about right. You have some people who understand everything, the majority above 80%, and a few less than 80% or less than half. So what I would recommend if you are less than 80 or less than half is read, so the textbook, of course, where you have also all the information. And of course, you can ask questions. You can ask your TA in the exercise session. You can ask on the forum, then everybody benefits. You can send an email to the TAs or to me, and we can help you, right, if there is anything that is not clear. Right, this is what we are here for. All right, but this is good. It means that the speed is about right. So yes, I see a question over there. Maybe we can... There you go. Oh, sorry, almost.
I'm a little confused with the terminology because we say block storage versus object storage, but I feel like in the textbook we say that Azure is both object storage and thus use block storage.
Yes, it's true. Here the terminology is a bit fishy. What I mean is the notion of object storage, typically as opposed to file storage, you mean that there is no hierarchy. Right? In file storage, you have a hierarchy with directories and files, and then you call them files, right, with the hierarchy. If there is no hierarchy and it's all flat, it's just a key that identifies as an object, then you call it object storage, and you just have black boxes, right, where it's associated with a key, but then there is no directory. Traditionally, when we talk about object storage, there was no blocks in there. traditionally the blocks were rather with the file storage. So either you had a hierarchy and the files are stored in blocks, or you have object storage with a flat naming and without any blocks, right? And so this is why I tend to contrast the two. But Azure is the Azure Blob Storage is very special because it's kind of in between, right? It's object storage because you don't have a file namespace, you don't have directories, but at the same time it uses blocks, right? So it's in between. So I don't know if that helps, but this is basically how it is, right? And so this is why I tend to contrast object storage with block storage. Maybe if I want to improve it further, I could, instead of saying here a block storage over block object storage, I could say block storage over not using blocks, right? To make it simpler, right? I think it's probably a better idea to contrast object storage with file storage, the notion of hierarchy, but not with the notion of blocks, right? So that is a good point, and I will probably update that slide to make it clear, right?
Maybe as a short follow-up, I'm a little confused because I feel like the file hierarchy doesn't determine anything in the Hadoop file system model, and the files itself, like the data, isn't really in this file hierarchy order. It's just how we store the IDs of the blocks. And I feel like it doesn't really make a difference if we store the block, like the mapping from where it is to the IDs in a tree structure or in a map structure. And it feels like there's so little difference, and that Hadoop is also using a flat layout because the data is flat.
Mm-hmm. So there's two things in there. First, I think that the benefit of a flat layout is that it's very easy to scale. And that we've seen with DynamoDB, right? With Dynamo. When all is flat, you can just, you have load balancing, you have the hashes of the keys on the ring and so on. It's very easy to spread it all over. The moment you start introducing a hierarchy, and I mean a real one, not just emulating the slashes, a real hierarchy, then this is what starts introducing a single point of failure, because when you have the hierarchy, it needs to be stored somewhere. And then this is why you have the name node that centralizes things in HDFS. So this notion of having a file namespace is kind of associated with the notion of having a centralized architecture. Of course, you can then federate and have multiple name nodes and so on, but this is kind of the intuition, right? So when everything is just flat, it's very easy to spread over a huge amount of machines. When you start adding a file system and a hierarchy, then it starts needing some centralization, right? That is the intuition. In fact, this is why Azure splits it in two, because Azure also has something called Azure Data Lake Storage, I think, Azure Data Lake. And Azure Data Lake does have a hierarchy, like a file system, and it is implemented on top of the Azure Blob Storage, right? So the Azure Blob Storage takes care of storing all of the files, but then the file system is handled separately, and then it gives you a full data lake, right? That is the idea. Did it help, or did I confuse you even more?
Thank you.
It helped? Awesome. And again, that happens often, that there are things that are historically associated, even though technically they need not be. And that's the example between the notion of object versus file and the notion of block or not block. There is a historical association that you have blocks with when you have files, and you don't have blocks when you have objects, but it's not 100%, because, and Azure Blob Storage is then the counterexample. There's another example of that, I remember a head TA back then mentioned it a lot. When we say OLAP, OLAP means online analytical processing. And in many people's minds, when you say OLAP, they think data cubes. For whom is that the case, that they would think data cube when we say OLAP, right? It's kind of an association. But when you think of it, this association is technical. It's historical, it's not technical. Because you can also call it OLAP when you have trees or any other data shape, because what OLAP is really about is that it's read intensive. This is what OLAP really means. But historically, you have this association with data cubes, also similar to this, right? So thank you for the question. Anybody else? Any other questions? Yes, over there, maybe we can, in small hops, not a single go, because, yeah, very small hops. There you go. We take our time. We have time. We have time. Yeah. All right. Go ahead.
Yeah, I had one question about like the when we were switching the name nodes. So when one name nodes fail, I remember in the previous lectures we read that the mapping of the object ID versus where it is stored is not essentially persisted inside the name node, like which data node that particular object ID belongs to. So while we were building checkpoints, my question was why don't we store that location as well? Because it's like very frequently changing, or is it some other reason?
Yes, so you're basically suggesting an alternate design in which that's probably a discussion that actually took place when they introduced the early versions of the system in which they had the namespace file and the checkpoint name node that was actually doing that. And they probably then had these two routes, right? How can we go? And I think it's perfectly reasonable what you indicate that you could also persist for efficiency reasons, the mapping from the block IDs, not object IDs, right? Block IDs, from the block IDs to their block locations. You could persist it, and then when you restart the name node, it's already there, and you can just take it from there. They probably had this discussion. It was probably in the discussion. There might have been pros and cons. I don't know if there can be any staleness or anything if there are writing operations still going on. I don't think it would be a big deal. But they probably, so the other route would be to have the other nodes, additional nodes, and then they sync over this Quorum Journal Manager or over the network data storage, right? And so what I think happened is that probably, I'm just speculating here, right? But probably they discussed it. It's probable somebody suggested that. But once you have introduced these standby name nodes that are there and take over immediately, then you agree it's no longer needed, right? So then you don't need to do it anymore, right? Because the standby name nodes, they receive also the reports. They have all the information, including the mappings, right? Right. But it's good to put yourself in the shoes of the engineers, right? Because now I directly give you the solution, like how this is done, but this took decades to do, right? And so of course the engineers, they had to solve these problems and they had to come up with ideas and made some design decisions that could be made differently. Maybe some of you will build new systems that might change these assumptions, or you might discover that doing it differently actually brings an advantage. And it's going to be exciting in the next couple of years, right? If there's new systems. Right. Did I answer your question?
Yep.
Yes. Anybody else? Any questions? On Zoom, any questions? Anybody? Nobody on Zoom? All right.